Custody transfer requirements. The custody transfer standards for liquids ensure that the transferred liquid is accurately and reliably measured. The total quantity, referred to specified conditions, of fluid transferred must be accurately recorded on a continuous pipeline or batch ship-loading basis. As the product temperature and hence density changes, the effects of temperature must be taken into account by referring the actual measurement of flow volume to a specific reference temperature, or by inferring the mass of liquid by relating the measured flow to the liquid density. This is done by measuring the actual flow temperature or density and performing an agreed standard calculation. This calculation and the associated metering accuracies are governed by the custody transfer agreement between the parties concerned. Haver standards and agreements. A typical contract may define a specific measurement standard, such as the American Petroleum Institute, API, Petroleum Measurement Standards, or an OIML standard that is tied to the International Standards Organization, ISO. These standards include all the equipment required and details on the process to achieve an acceptable level of measurement. Calibration and proving. In addition to accurate metering to custody transfer standards, each metering installation must be equipped with a system for periodically checking the system calibration. This system is known as a meter prover, and the selection of an appropriate prover for each type of installation and the associated proving regime is also covered in this document. System uncertainty. The highest standard recognized by the International Organization for Legal Metrology, OIML 117, requires a minimum system uncertainty of plus 0.3% over a wide operating range. For large volume transfers, better accuracy is required, so the systems are proven over a narrower range of operating conditions and typically achieve a plus 0.1% extended uncertainty, the same as a system using API standards. A good API system would typically have a plus 0.1% extended uncertainty. These requirements ensure that the custody transfer metering systems are capable of providing precise and reliable measurements, critical for accurate and fair transactions between parties involved in the transfer of liquid commodities. End user requirements. Metering system. The metering system must meet various technical and operational standards to ensure accurate and reliable measurement of liquid transfers. Below are the detailed requirements. Meter accuracy requirements. Standards, defined by the American Petroleum Institute, API, MPMS 12.2, Manual of Petroleum Measurement Standards, Chapter 12, Calculation of Petroleum Quantities Measured by Turbine or Displacement Meters. Terms. The publication defines terms like run tickets, receipt and delivery tickets, and others, selecting standardized terminology. Equations. Specifies the equations for computing correction factors, rules for sequence, rounding, and significant figures in calculations. Tables. Provides tables convenient for manual and computer calculations. Reliability requirement. Availability. The pipeline custody metering system and ship loading systems must exceed 99.9% availability. The supplier must provide reliability data and calculations to verify this requirement. Pipeline integrity monitoring. Custody monitoring. Both ends of the pipeline must be custody monitored to detect leaks by comparing standardized flow rates. Identical measuring systems at both ends eliminate spurious differential effects. Documentation. Refer to the Pipeline Leakage Detection Study for further details. Metering system configuration. SCID package. Each system must be a fully piped, cabled, instrumented, and pre-calibrated SCID package. Multiple meter runs plus a spare are required for high capacity and turndown. Features. Each SCID should include full sunshade and hoist facility, common meter prover, various components such as gate valves, strainers, flow meters, temperature and pressure transmitters, and more. Meter skid, components, flanged skid edge prover, inlet header, fast loop grab sampler for specific skids, densitometer with pump motor, valve and temperature measurement, inlet gate valve with electric actuator, simplex strainer with differential pressure indicating transmitter, thermal relief valve and drain valves, custody transfer flow meter, temperature and pressure indicating transmitters and gauges, flow balancing control valve with electric actuator, high integrity double block and bleed prover, takeoff and outlet valves with electric actuators, Flanged outlet header and skid edge drain header. Prover type. Each metering skid should have one prover run or standard meter, preferably a permanent fixed bidirectional prover controlled by a dedicated prover control microprocessor. Components: 4 detector switches, asymmetric limit switch arrangement to ensure accuracy, designed to prevent cavitation at design flow rate, flanged field recalibration connections for easy hookup of mobile calibration equipment. Calibration: initial calibration to be performed at the supplier's works using the water draw method with clear, deaerated water. These requirements ensure that the metering system is capable of providing precise, reliable, and secure measurements for custody transfer applications in various operational conditions. Flow computers requirements. General requirements. Dedicated systems. Each meter run must have a dedicated redundant flow computer, and each prover must be controlled by a dedicated redundant control microprocessor. Installation. Flow computer prover control microprocessors, supervisory computers, SCADA, and printers should be installed in designated control rooms. Reliability. Designed to the highest standards of reliability, capable of interfacing with primary devices to provide readouts of meter run parameters and data in prescribed units. Redundancy in memory. Microprocessors should be redundant and equipped with non-volatile memory to maintain critical parameters for at least 30 days on AC power failure, or alternatively with an integral battery backup. Inputs and outputs. Minimum inputs. Custody transfer flow meters, prover position limit switches, smart differential pressure transmitters, smart temperature transmitters analog mode, smart pressure transmitters analog mode, densitometers, motor-operated valve position switches. Minimum outputs. Redundant RS-422-4485 Modbus RTU serial link for SCADA communication. Connection capability to supervisory computers. RS-232 serial link for printer communications. Totalizer outputs for non-resettable electromechanical digital totalizers. 4 to 20 milliamp analog outputs for control purposes. Flow computer capabilities. Visual indication. Provide visual indication of all process measurements and current system status. Operator interface. Include a manual operator interface with a keyboard, screen, and pointing device. Security. Ensure at least 3 levels of data and input security via key switches, passwords, and mechanical seals to prevent unauthorized adjustments. Calculations. Calculate run flow rates and totalized flow from flow meter input signals. Use line temperatures, pressures, and header densities to calculate mass flow rates, mass totals, and correct volume flow rates and totals to standard conditions. Default and alarms. Revert to default values on input transducer failure and trigger alarms. Suppress flow totalization and transmission during calibration mode. Data storage. Store totalized information and critical coefficients to detect and correct limited memory failures. Alarm logging. Log all abnormal conditions affecting system integrity or accuracy with time and date stamps and print them. Data handling. Record all raw input values, MA, frequency, etc. Record scaled inputs in engineering units. Store all constants, intermediate results, and final results used in flow calculations. Enable communication with the station totalizer prover microprocessor for transferring selected measured and calculated variables, status, and alarm signals on demand. Prover computer capabilities. Automatic sequences. Perform automatic proving sequences as defined in applicable codes and standards. Security. Provide at least 3 levels of data and input security via key switches, passwords, and mechanical seals. Prover control. Capable of controlling the prover by initiating valve movements and receiving sphere detection pulses. Fault detection. Monitor all signals for faults or out-of-tolerance conditions during proving. Abort proving sequence and suspend calculations if any fault is detected, and trigger alarms. Volume selection. Allow manual selection of prover base volume with status indication to the prover computer. K-factor updates. Download new K-factors to the appropriate flow computer upon successful proving sequence and operator confirmation. Parameter input. Enable manual input of parameters via keypad, including coefficient of thermal expansion for the fluid, default values for input transducer failure, alarm parameters, minimum flow rate per meter, ship identification and loading capacity. The supervisory computer system must be capable of providing the current metering and alarm reports as detailed below. Data for these reports should be held in memory and downloaded on demand. Reports shall be printed on the system printer either automatically or on demand, ensuring information is held in memory until overwritten by new data from future runs. The types of reports include status report, skid report, interim skid reports, meter proving reports if applicable, alarm report, current daily status report, 7-day mass totals, parameters report, ship loading report. These comprehensive requirements ensure that the flow computers and associated systems provide accurate, reliable, and secure metering and reporting capabilities essential for custody transfer operations. Type approved custody transfer meters, direct volumetric flow meters, types. The custody transfer meters should be direct volumetric flow meters, including turbine meters and positive displacement PD meters. These meters directly measure the volume of liquid passing through them. Inferential flow meters. Inferential flow meters, such as ultrasonic and Coriolis meters, should also be considered for custody transfer applications. These meters infer flow by measuring other properties such as velocity, ultrasonic, or mass, Coriolis. Pipeline characteristics. Compatibility. The selected meters must be compatible with the specific characteristics of the pipeline, including size, pressure, and temperature conditions. Product characteristics. Fluid types. The meters must accurately measure the types of fluids being transferred, considering factors such as viscosity, temperature, and density variations. Flow range. Measurement range. The meters must handle the full range of flow rates expected during operations, from minimum to maximum flow conditions, ensuring accurate readings across this spectrum. Viscosity range. Fluid viscosity. The meters must accommodate a range of fluid viscosities, ensuring accurate measurements for both low and high viscosity liquids. Wax. Handling waxy crudes. Meters must be capable of handling waxy crude oils without significant measurement errors or operational issues. Measurement turndown. Turndown ratio. The meters should have a high turndown ratio, enabling them to measure accurately over a wide range of flow rates. A turndown ratio of 10:1 or better is typically required. Rangeability. Operational flexibility. The rangeability of the meters should support various operational conditions, maintaining accuracy and reliability across different flow rates. Meter factor, K. Calibration factor. The meter factor, K, must be determined through calibration, ensuring the meter's accuracy in converting the raw measurement data to standard volume or mass units. These detailed requirements ensure that the custody transfer meters used in the metering systems are accurate, reliable, and suitable for the specific operational conditions they will encounter. Positive displacement meters. Operating principle. Direct measurement. Positive displacement, PD meters directly measure the volume of liquid passing through them by trapping a fixed amount of fluid and then releasing or displacing it. Mechanical components. PD meters use mechanical components such as pistons, gears, or vanes that move as the fluid flows, turning the movement into a volumetric measurement. PD meter accuracy. High precision. PD meters are known for their high accuracy, typically achieving an error margin of by 0.1% to 0.2% under stable flow conditions. Viscosity range. They maintain accuracy across a wide range of viscosities, making them suitable for various fluid types. Calibration. Regular calibration is essential to maintain accuracy, especially when there are changes in fluid properties or operating conditions. Advantages of PD meters. Accuracy and repeatability. PD meters provide high accuracy and repeatability, making them ideal for custody transfer applications. Low sensitivity to flow profile. These meters are less affected by changes in flow profile compared to other types of meters. Broad range of applications, suitable for measuring a variety of fluids, including viscous and non-lubricating liquids. Disadvantages of PD meters. Mechanical wear. The mechanical components are subject to wear and tear, requiring regular maintenance. Pressure drop. PD meters can cause a significant pressure drop in the system, which might not be suitable for all applications. Size and weight. They tend to be bulkier and heavier compared to other flow meters, which can be a limitation in some installations. PD meter performance. Flow range. PD meters perform well across a wide range of flow rates, but may require multiple meters in parallel to handle very high flow rates. Installation considerations. Proper installation is crucial to ensure accurate measurement, including alignment and support to prevent stress on the meter. Environmental conditions. PD meters must be protected from extreme environmental conditions to prevent damage and ensure longevity. These core technical parameters ensure that positive displacement meters are capable of providing accurate and reliable measurements, making them suitable for a variety of custody transfer applications in the oil and gas industry. Operating principle. Axial flow design. Custody transfer turbine meters typically use an axial flow design, where flow rate is determined by measuring the angular velocity of a bladed rotor suspended in the flow stream. Types. There are two main types of axial flow turbine meters used in custody transfer applications: conventional multi-blade turbine meters, helical turbine meters. Conventional turbine meters, rotor design. Conventional turbine meters feature a multiple-bladed rotor design. The rotor blades can be straight or helical, and some line sizes and fluid applications may include a rotor rim. Bearing types. The type of bearing used in conventional turbine meters can vary and includes ball, journal, and hydraulic bearings. Helical turbine meters, rotor blade. Helical turbine meters have a two-bladed helical rotor, allowing for accurate measurement of higher viscosity liquids due to the reduced effect of the stagnant boundary layer on the rotor surfaces. Bearing design. These meters typically use a journal bearing design. Boundary layer effects. The helical design minimizes the boundary layer effect, which significantly impacts the accuracy of conventional turbine meters. Technical parameters and advantages. Both conventional and helical turbine meters are designed to provide high accuracy in measuring flow rates. Viscosity handling. Helical turbine meters are particularly effective in handling heavy, high-viscosity crude oils and other challenging fluids, making them suitable for a broader range of applications compared to conventional designs. Reduced sensitivity. Helical meters exhibit less sensitivity to changes in the boundary layer thickness, improving measurement stability and accuracy. These detailed technical parameters and design features ensure that turbine meters are highly effective for custody transfer applications, providing reliable and accurate measurements across a range of operating conditions and fluid types. Helical turbine meters. Advantages of helical turbine meters. Higher turndown range. Helical turbine meters offer a higher turndown range on high-viscosity crudes compared to conventional turbine meters. Excellent repeatability. These meters provide very good repeatability, ensuring consistent measurement accuracy. Reduced susceptibility to fouling. They are less susceptible to fouling, abrasives, and deposits, making them suitable for a variety of fluid conditions. Viscosity tolerance. Helical turbine meters are less sensitive to changes in fluid viscosity, maintaining accuracy across a wide range of viscosities. Lower pressure drop. These meters exhibit a lower pressure drop than conventional turbine meters, enhancing operational efficiency. Large size availability. Available in large sizes, helical turbine meters provide good value for high flow rates. Combined operating range. They cover the combined operating range for positive displacement, PD, and conventional turbine meter guidelines as stated in API MPMS. Robustness. Helical turbine meters are robust and can absorb minor damage without loss in performance, making them suitable for crude oil line integrity purposes. Insensitivity to filamentary material. The repeatability of these meters is insensitive to filamentary material and crude oil washing operations. Compliance with standards. Helical turbine meters satisfy all current API and OIML standards for custody transfer. Linearity. The linearity of helical turbines, MF versus Q, outperforms conventional turbines and capillary seal PD meters for flow rates greater than 3,500 bph. Performance with viscous fluids. Their performance is equal to PD meters over a range of low to high viscous fluids. Helical turbine meters have demonstrated good performance and reliability in various applications, including those in Europe and the North Sea. These advantages make helical turbine meters a preferred choice for measuring high-viscosity crudes and other challenging fluid applications, ensuring accuracy, reliability, and operational efficiency. Coriolis mass flow meters. Coriolis mass flow meters operate based on the principle of Coriolis force. The meter consists of a vibrating tube through which the fluid flows. As the fluid moves through the vibrating tube, it experiences a twisting force proportional to the mass flow rate. This twisting force causes a phase shift in the vibration, which is detected by sensors and converted into a mass flow measurement. Proving Coriolis mass flow meters. Coriolis mass flow meters are proven using standard procedures, such as water draw methods, comparison with a reference meter, or by using a master meter. Proving ensures the accuracy and reliability of the meters in actual operating conditions. Calibration should be performed under conditions that replicate the actual process as closely as possible. Coriolis meter performance. Coriolis meters provide direct mass flow measurement, unaffected by changes in temperature, pressure, or viscosity of the fluid. They offer high accuracy and repeatability, making them suitable for custody transfer applications. Performance metrics include accuracy, typically about 0.1% of the mass flow rate. Repeatability, 0.05% of the mass flow rate. Turn-down ratio, up to 101. Sensitivity to entrain gas, minimal, but specific models can handle some levels of gas entrainment. Advantages of Coriolis meters. Direct mass flow measurement, high accuracy and repeatability, independence from fluid properties like viscosity and density, no moving parts, reducing maintenance requirements, can measure mass flow, density, and temperature simultaneously. Disadvantages of Coriolis meters: higher initial cost compared to other meter types, sensitivity to installation conditions such as vibration and stress, potential issues with fluids containing high levels of entrained gas or solids, larger size and weight, especially for high-flow applications. Application of Coriolis meters. Coriolis meters are widely used in various industries for custody transfer, process control, and monitoring applications. They are suitable for crude oil and refined petroleum products, chemicals and petrochemicals, food and beverage industry, pharmaceuticals, natural gas with special considerations for gas entrainment. Ultrasonic transit time liquid flow meters. Ultrasonic meters derive flow rate by measuring stream velocity through a calibrated cross-sectional area. Volume throughput is then calculated by multiplying the velocity by the flow area as shown by the following equation. Text volume throughput Q equals text velocity V times text area A. The flow area can be accurately determined from measuring the average internal pipe diameter in the measurement area. The velocity is determined by measuring the difference in transit time of high-frequency sound pulses that are transmitted along and against the flow stream. The pulses are generated by piezoelectric transducers that are positioned at an angle to the flow stream. TASH, ultrasonic meter performance. Ultrasonic meters measure flow with a high degree of accuracy using multiple beams and digital signal processing. They have no moving parts, requiring little or no maintenance. Ultrasonic meters do not obstruct or slow the flow of liquid through a pipeline. They can accurately measure a broad spectrum of liquefied petroleum products without having to be proven, as is the case with mechanical technologies. Ultrasonic meters are sensitive enough to detect the smallest leaks in a long pipeline and can measure and compensate for the many variables that can affect accuracy in custody transfer applications. Installation of ultrasonic transit time flow meters. Proper installation is critical for accurate measurement. Transducers should be mounted at locations where the flow profile is fully developed and free from disturbances such as bends, valves, or pumps. Installation should follow the manufacturer's recommendations for straight pipe lengths upstream and downstream of the meter. Proving liquid ultrasonic flow meters. Proving involves comparing the ultrasonic meter's readings with a known standard, typically using a meter prover. Proving ensures that the ultrasonic meter's accuracy remains within acceptable limits under actual operating conditions. This process may be conducted periodically to verify and maintain measurement accuracy. Advantages of ultrasonic meters: high accuracy and repeatability, no moving parts resulting in low maintenance requirements, minimal pressure drop, capable of detecting small leaks, suitable for a wide range of liquid applications. Disadvantages of ultrasonic transit time flow meters. Performance can be affected by the presence of gas bubbles or solid particles in the fluid. Higher initial cost compared to some other flow measurement technologies. Requires careful installation and alignment of transducers. Sensitivity to changes in flow profile and pipe conditions. Application of ultrasonic transit time meters to transportation of high flow rates of crude oils. Ultrasonic transit time meters are well suited for high flow rate applications such as the transportation of crude oils. Their ability to handle a wide range of flow rates, coupled with high accuracy and low maintenance, makes them ideal for such applications. They provide reliable measurements necessary for custody transfer, ensuring compliance with industry standards, and minimizing measurement uncertainties.